Hello everyone. So now we're on to the sixth problem on my final exam in analysis in one variable. And that is, we have a function, f of x, that is differentiable and its derivative is decreasing. For the first part of the problem, we're supposed to prove this inequality here. So, firstly, I wanted to give you a mental image of what this problem actually means. What do we have here on our right hand side? If you may be familiar with Taylor polynomials, this might look like a first order Taylor polynomial, right, of f of x centered at a. And you would be completely right, except you don't have the error term. That doesn't really matter. So essentially what we have here is that, okay, so we have some kind of function, right? And since the derivative is increasing, it can never like scoop upwards, so to speak. So maybe it goes something like this. The derivative here is strictly decreasing. So what would this mean? This would mean that for any a, for our a here kind of means where we're doing our linear Taylor polynomial from, and then the x is just the rest of the function basically. So if I were to choose this point, then what would my Taylor polynomial look like? Of course, it would just look like this. You get the tangent line of that function in that point. And here, as you can see, they're equal at precisely the point I chose, but at all the rest, everything is below this graph. So yeah, that was the mental image, and now for the actual proof. So you could do this in various ways. You could move everything to left-hand side and then look at the derivative, of course, and then find out that, oh, that is also less than something, and then work your way from there. What I would prefer in this case is just using the mean value theorem. Yeah, okay, so firstly, yeah, that's what I'm going to do. But firstly, we need to look at some cases. Okay, so I have case one, of course, that is just case one, x is equal to a. Then it's just obvious. Everything is, that becomes 0. F of x is equal to f of x. That is true. Case 2, x is greater than a. Then we can rewrite this whole thing as, because we're dividing by x minus 1, and if x is greater than a, then that whole parenthesis is greater than 0. So therefore we can rewrite this as f prime of a is equal to f of x minus f of a divided by x minus a. And what, greater than, yes, exactly, greater than. And what do we know about this? Well, we know that there exists a c in between x and a, such that this is equal to f prime of c, where c, as I just said, is between a and x, because now here x is greater than a. And what can we say about this? Okay, so we have f of a, f prime of a is greater than or equal to f prime of c, where a, and this of course implies that c is greater than a. And if f prime is decreasing, then that inequality holds, because of if as I said, if c is greater than a, then f prime of c is then of course less than f prime of a. So that is our second case, and then our third case is x is less than a. What do we have then? Okay, we can then rewrite the exact same thing except with the opposite. So when we're dividing by x minus a, we have to flip the greater than or less than sign. So therefore, we now get f prime of a is less than or equal to f of x minus f of a over x minus a. Yes, and of course now we do exactly the same thing. So now we know that there is there's a c in between now, not a and x, but x and a. So in c in between x, because now x is smaller than a, which means that c is greater than a. And then the exact same logic for this one also applies. Now, instead of, no, sorry, c is less than a, sorry. C is less than a. So then, of course, f prime of c is greater than f prime of a. So yes, that was the first part of the problem. And now we're moving on to the second part. But first, give me a second. So now, okay, so this is our problem here, the second part. So we're supposed to prove that f of a plus f of b minus f of a divided by b minus a times x minus a is less than f of x for all x in the interval a to b. And now, to do this, we denote a help function. We call it age of x. And this thing here, and we want to show, sorry, and this thing here is equal to f of a plus f of b minus f of a over b minus a minus f of x. And we want to show that this thing here is always less than or equal to 0. Oh, sorry, I forgot the times. So this is our help function now. I just moved everything onto this left-hand side, and we want to show that this thing here is less than or equal to 0. So how do we do this? We start by taking the derivative with respect to x. So this thing here disappears. This becomes just 1. So this, we only get the coefficient left. F of b minus f of a over b minus a, and then minus f prime. Yes, so that's the first thing. And then we also note that, okay, so firstly, we note that age of a is equal to 0. So that one is good. And we also look at age of b. What is that? Okay, so then we have this thing here stays the same, and then we have b minus a, so these two disappear. And then we have f of a plus f of b minus f of a minus f of b. So this thing here is also 0. So now we can look at this thing in a whole new light. So we have our function here, and we know that in our interval, in our only relevant interval, of course, in between, say, a and b, we know that, okay, both of them are 0. So if we just can prove that it looks something like this, then we're done. So what can we say about this thing here? Okay, again, we use the mean value theorem. So we know that there exists a c in between a and b. I'm not even going to write it out, such that this is equal to f prime of c minus f prime of x. So now, okay, we have this thing here. And what do we know about f prime? We know that f prime is strictly decreasing, meaning that this thing here, I'll move it over here, we know that this, so f of x, if f prime is decreasing, then if x is, say, greater than c, then f prime would be less than, and because we're doing the subtraction, we have that this thing here is larger. So we imagine, okay, we have this minus that is a positive distance. So this thing here is greater than 0 if x is greater than c. And we also know that it's less, and the opposite also holds, it's less than 0 if x is less than c. So we know that, okay, we have 2 points here, and we know that it's equal to the if x is equal to c, that then implies that it's, yeah, this thing here is equal to 0. So therefore, we have 2 points where it intersects the x-axis, and we know that there's only 1 point where the derivative is 0. So therefore, we know that the function is strictly below the line. So yeah, and that was everything. I think that proof is conclusive, at least according to my professor it was. So yes, that was everything. So, thank you so much for watching. And oh yeah, sorry, I forgot something. Wait. And the third one was to interpret these inequalities graphically, and then you draw some sketches with some functions where the derivative is decreasing, so it looks kind of like this. It goes down. It's like a sad parabola. You get the point, yeah. And then you just draw some pictures and point out a and b and see that, oh, it's always less than. Yeah, I don't even know why. Yeah, for the first one, the answer was basically what I said in the beginning, that you make the tangent line, and the tangent line is always greater than if the function which you took the tangent line of is if its derivative is decreasing. So yeah, that was basically everything for me. Hope you enjoyed the video, and I will see you some other time. Have a good one. Bye bye.